Hi, this video is to help you through the activity on binary covalent compounds. Last time we talked about ionic compounds and how to name them. Notice that in the table on your activity that all of the ionic compounds have a metal and a nonmetal. On the other hand, covalent compounds have all nonmetals. Now, the ionic compounds are formed by transfer of electrons from one of the elements to the other, or basically from the cation to the anion, or they can be thought of as compounds made from electrostatic attractions between an anion, which has a negative charge, and a cation, which has an opposite positive charge. On the other hand, the covalent compounds are not made of cations and anions like the ionic compounds are. The word covalent means sharing or bonded. All of the elements in these formulas are bound together and they obtain their full octets through sharing electrons. This semester, we're going to learn how to name covalent compounds. For today though, we're just learning how to name binary covalent compounds. The word binary just means two, and so the binary covalent compounds that are listed here are everything except this one. So this molecule has 3 different nonmetal elements in it, and this is not what we're going to be naming today. So we are not going to learn how to name this kind of molecule yet. We're only going to be focusing on the binary covalent compounds. So the element or the compounds that have only 2 types of elements in each one of their formulas. As a review, I just want to remind you how we were naming ionic compounds. Whenever you're naming an ionic compound, you first name the cation. If it's a transition metal, you use Roman numerals to show the charge on the transition metal. And then you write the name of the anion. If it's an elemental anion, you use the IDE suffix. So here are a list of ionic compounds. These are elemental ionic compounds and their names. And let me remind you that we also talked about naming complex ions. The rules are the same. The one difference is that if you're naming an ionic compound that has an ionic anion, for example, sulfate, you don't need to use the IDE ending like you do here. So only elemental anions get the IDE ending. When you're naming anything that has these complex anions in it, you just use the name of the anion. So that's what is written right down here. Don't use the IDE ending when naming complex anions. One important difference of naming ionic compounds and covalent compounds is that in ionic compounds, we don't use a prefix system. In the covalent compounds, the binary covalent compounds, we will be using a prefix system. And here it is. So please look at the rules for naming binary covalent compounds that are listed in your activity. Notice that we're talking about this prefix system. These are Greek prefixes for anywhere between 1 and 10. So I've listed for you in this little box a couple of the common binary covalent compounds that you will see very often. And I also want to point out that these things have common names. I'd like you to know the common names for these 3 compounds, but we'll also name them using the systematic name. So the systematic name is kind of like the long formal name, and these common names are like little nicknames that the molecules have. You probably already know that this is water. NH3 is ammonia, and CH4 is methane. But we can also talk about the systematic names. So when you're naming something in the systematic system, you basically just take the name of the element and you name it, and then you use the prefix system to say how many there are, and then you name the second element and you use the prefix system to say how many there are, and you always end the second element in IDE. The only caveat is that for the first element, you never use mono. So for example, CH4, it might be tempting to name this monocarbon tetrahydride, but you never use mono for the first element. So you drop that, and this would just be called carbon tetrahydride. So you just name the first element, you use the prefix unless it's mono, and you drop it, And then you name the second element using the prefix to say how many there are, and you always end the second element in IDE. Let's do ammonia. So this is NH3, so you would name it nitrogen trihydride. And then for water, this would be dihydrogen, so this di is the prefix for this, and monooxide because there's one. So do not drop the mono if it's for the second element. All right, at this point, it's a good idea to pause the video, reread the rules, and then try to answer the questions that follow on this part of the activity. I'd like you to come up with your own flowchart for the main differences between naming ionic compounds and binary covalent compounds, but I'll show you what I've got, just in case you forgot anything. So if you come across a binary compound, the first thing you want to ask yourself is it ionic or is it covalent? Because you use two different naming systems, depending on whether it's ionic or covalent. If it's ionic, then you don't use prefixes. You name the cation first, use Roman numerals for a transition metal, and then name the anion last. And if it's an element, use the IDE suffix. Now, if it's ionic, you know more than just binary ionic. You know how to name most ionic compounds at this point. If it's a binary compound and it's covalent, then you know how to name it using the prefixes. So you name the first element using the prefix to tell how many atoms there are, except for mono. You drop the mono if it's the first element. And then you name the second element using the prefix to tell how many elements there are, and you name that last element using the IDE suffix. So those are the two naming systems we know. We know how to name ionic compounds in general, and we know how to name binary covalent compounds. So now I'd like you to practice, if you haven't already, practice by completing the table. I recommend that the first thing you do is label these as ionic or covalent so that you know which naming system to use. If you need to, pause the video now. Otherwise, we'll go on. So I will label these things as they are. I know that this is ionic because it contains a metal and nonmetals. And I know that the things that I've labeled covalent are covalent because they only contain nonmetals. So nonmetals only, nonmetals only. This one's ionic because it contains a metal and nonmetals. Covalent because it only contains nonmetals, and then once again, a metal plus a nonmetal, so that's ionic. Okay, so now this is ionic. This is a formula that contains a transition metal and a complex ion, the hydroxide ion. So I would name this, I'd first have to find the charge on copper. And because hydroxide ion has a -1 charge, that must mean that copper has a +1 charge. So this is copper 1 hydroxide. Nitrogen trioxide, just 1 nitrogen and 3 oxygens, it's covalent. This is sulfur hexafluoride, so the hexafluoride. This is an ionic compound, once again, that has a complex ion. The name of this complex ion is hydrogen phosphate. You could tell this from flipping to the table in the previous activity that listed some of the complex ions. Hydrogen phosphate has a 2- charge, and that's why there's a 2 here. But anyway, this is potassium hydrogen phosphate. And then dinitrogen pentachloride would just be 2 nitrogens, 5 chlorines. This would be nitrogen trihydride or ammonia. This is the common name, but this is the systematic name. And then copper 2 oxide. The copper has a 2+ charge, and that's what this Roman numeral is telling you. And the oxide also has a 2- charge, so the 2's basically cancel each other out and you get copper oxide. Just 1 copper and 1 oxygen. All right, so now that we know the naming systems for both ionic and binary covalent compounds, we're going to move on and talk about Lewis structures. So we're going to switch gears and talk about how to draw structures. We're going to start at Lewis dot structures. And these are basically little symbols that tell us how many valence electrons are in an element. So you need to take out your periodic table and you need to be able to recognize how many valence electrons each element has. And you'll represent the valence electrons by little dots around the outside of the symbol. I recommend that you do it in a way so that you show the maximum number of unpaired electrons possible. And so I'll show you how I do it. For neon, I would look at my periodic table and find that neon was in group 8A of the periodic table, which means it has 8 valence electrons. So I imagine that the neon symbol has 4 sides, just like a box, and I'll put 1 electron on each side of the box, and then I'll go around again and put 1 electron on each side of the box. So this shows that I have 8 electrons around neon, and I think of them as being in 4 pairs here. Each pair is on each side of the box. Okay, so that's the Lewis dot symbol for neon. Now let's do fluorine. So the atom fluorine is in group 7A, and so it has 7 valence electrons. So I put those electrons around the outside, and then I pair them up. And so now I have basically 6 electrons that are in pairs here, and then I have 1 lone electron on this side of the box. Now, the nice thing about these Lewis dot symbols is that they really show you how many electrons are needed, because I need 1 more electron, right, to make this fluorine happy, which is why fluorine would usually make a -1 anion, because it would get an extra electron from something else. Now, the number of electrons that an element needs is also equal to the number of bonds it will make. So that's a useful thing to keep in mind. I'll remind you of that in a minute. But from this Lewis dot structure, I can see that fluorine needs 1 more electron, and that means it will make 1 bond in a covalent compound. Now let's do oxygen. Oxygen is in group 6A, and so it has 6 valence electrons. And so I'll go around the outside, and then I'll start pairing them up. And this is not the only valid Lewis dot symbol, but this is the one that would help you see that there are 2 single electrons, and so there are 2 electrons that oxygen needs to make a complete octet. And that means that oxygen will make 2 bonds. It doesn't matter where you put these single electrons, and you could technically also pair them. But I recommend doing it in this way, where you're basically putting them as single dots, and then you go around again and pair them so that you have the maximum number of unpaired electrons in your dot symbol. Now let's do nitrogen. Nitrogen has 5 electrons because it's in group 5A. And if you draw nitrogen so that it has 3 lonely electrons, then you can see that it needs 3 electrons to make its octet, and it will also make 3 bonds. And then carbon is in group 4A, so carbon has 4 electrons, and I again recommend that you put all 4 of those electrons as single dots, and you can see then that carbon will make 4 bonds, or it needs 4 electrons. Now I'd like you to pause the video and try to draw the Lewis dot symbol for chlorine, and then try to represent the chemical reaction that's underneath using Lewis dot symbols. Once you've given that a try, go ahead and unpause the video. All right, here's the Lewis dot symbol for chlorine. It would look just like fluorine. Basically, it has 6 electrons that are in pairs and 1 single electron. That means chlorine will make 1 bond. Now let's look at this chemical reaction. In this chemical reaction, you're starting off with 2 single chlorine atoms. So basically, if the 2 wasn't there, you would just draw a chlorine atom. And because the 2's there, you draw 2 single chlorine atoms. And they're becoming bonded. When they're drawn in a chemical formula like this, it means they're bonded together. So I would represent the 2 atoms individually like this. So they're 2 chlorines. And when they bond, they're going to share their electrons. So there are 2 ways that chlorine, or any atom, can fill its octet. It can either steal an electron and form an ionic compound, or it can share its electrons and form a covalent compound. So this chlorine here needs 1 electron to make an octet, and this chlorine needs 1 electron. So if the pink chlorine will share its electron with the blue chlorine, then they will have a shared pair. And it would look like this. So notice that I've put my pink chlorine here, my blue chlorine here, and the electrons that they're sharing are now purple. So one of the electrons came from the pink chlorine, one of them came from the blue chlorine, and now each chlorine has a full octet. So this chlorine has 2, 4, 6, 8 electrons, and this chlorine has 2, 4, 6, 8 electrons around it in its octet. So they're happy. They're holding hands. And this is why elements or atoms make bonds or molecules, because they want to acquire that full octet, and one way that they can do it is by forming bonds and sharing electrons. Now, this bonded pair of electrons can also be represented by a line. So this purple line represents 2 electrons that are shared between the chlorine atoms, and this line is exactly the same thing as writing this pair of dots between the 2 chlorine atoms. Remember that the number of electrons needed to make an octet tells you the number of bonds an element will make. This is really useful information because you can read the number of electrons needed right off the periodic table, and therefore you can read the number of bonds that an element will make right off the periodic table. If you know the chlorine is in group 7A and it needs 1 valence electron, then you know it needs 1 bond. Likewise, if you look for carbon and you know that carbon is in group 4A and it would need 4 electrons to complete its octet, then you know that carbon will make 4 bonds. In fact, carbon always makes 4 bonds. So before we go on to draw more Lewis structures, I would like to talk about the common bonding schemes for carbon. Carbon always makes 4 bonds, like we just said. So you can look at the periodic table and you can see that a carbon atom would have 4 electrons and it needs 4 more. And because it needs those 4 more electrons, it will always make 4 bonds. But there are several different ways that it can make 4 bonds, and these are the 4 ways that you can do it. So these are the 4 common bonding schemes for carbon. And these pictures are kind of a shortcut. You can imagine that there would be an element at the end of each one of these bonds, but I'm not showing those elements, I'm just showing the bonds. So imagine that there's something else at the end. So carbon can have 4 single bonds like shown here. And another way that carbon can have 4 bonds is by having 1 double bond and 2 single bonds. Or carbon can have 2 double bonds, still has 4 total bonds. Or it can have a triple bond and 1 single bond. So any combination of single, double, or triple bonds that will give carbon a total of 4 bonds is good. Because carbon needs to make 4 bonds, these will always be the common bonding schemes for carbon. Now, look for silicon in your periodic table. Notice that silicon is right underneath of carbon, and so silicon also has 4 valence electrons. Therefore, silicon will have the same common bonding schemes as carbon does. On the next page of your activity is this chart. And I'd like you to notice that this chart is organized in a similar way as the periodic table is organized. So we have group 4A elements, carbon and silicon. And notice how I've drawn this Lewis dot symbol of carbon so that it's very obvious that it needs 4 electrons and that it can make 4 bonds. These are the common bonding schemes of carbon, or the different ways that carbon can make 4 bonds. Silicon also has 4 electrons. It has the same Lewis dot symbol, except it's silicon instead of carbon. And it will also have the same bonding schemes as carbon. So in this box, you should write the same bonding schemes that you see for carbon. Basically, any combination of single, double, and triple bonds that will give silicon 4 bonds is okay. The group 5A elements have a Lewis structure that looks like this. 2 electrons in a lone pair and 3 single electrons. These elements need 3 electrons, and so they'll make 3 bonds. Now, any way that you can put 3 bonds on a nitrogen, any combination of single, double, or triple bonds, that also includes a lone pair, that is the common bonding scheme for nitrogen. So you should draw a very similar thing underneath for phosphorus. Group 6A elements have this Lewis symbol, and you can see that they need 2 electrons, so they will always make 2 bonds, and they will always have 2 lone pairs. So here are 2 ways that oxygen can make 2 bonds, and sulfur would have very similar bonding schemes. Hydrogen makes one bond, and so do all of the group 7A elements. So go ahead and fill in this table and pause the video now if you need to. In the next table, I'd like you to notice that this is specifically talking about the elements when they're in a covalent compound. So I'll go through this with you. The number of non-bonded valence electrons in hydrogen when it's in a covalent compound can be seen from this little picture. So notice there are no non-bonded electrons around hydrogen, and so I'd put a 0 here. The number of bonding valence electrons are the number of electrons in bonds. And when hydrogen's part of a compound, it has 2 valence electrons. In fact, this is why hydrogen makes a bond in the first place, so that it can fill its valence shell. So in hydrogen, you have 0 non-bonded electrons, 2 bonded electrons, and that gives you a total valence of 2, or a full shell for hydrogen. For carbon, the number of non-bonded electrons can be seen from up here. There are none. On the other hand, the number of bonding electrons is 8. So there are 2 bonded electrons in each one of the bonds, and so there are 8 bonded valence electrons. That gives you a total of 8 valence electrons. Once again, carbon is forming the bonds so that it can have a full valence of 8 now. So any of these other elements, hopefully you can guess that they will also try to fill their valence and get 8 electrons. So for nitrogen, hopefully you can see that there are 2 electrons that are non-bonded, and there are 6 that are part of bonds. That still gives you a total of 8 valence electrons. For oxygen, there are 4 non-bonded electrons, and there are 4 bonded electrons, giving you, once again, a total of 8. And for bromine or any of the halogens, there are 6 non-bonded electrons, 2 bonded electrons, and once again, a total of 8. The reason that these elements are forming bonds is to acquire a full octet or a full shell. And so hydrogen should always have 2 electrons when it's part of a compound, and any other element should have 8. Now that you understand these normal bonding schemes, I'd like to point out that these are the rules. Basically, carbon will always have 4, and so will silicon. Nitrogen and oxygen will always have 3 and 2, and hydrogen and the halogens will always have 1 bond. These are the rules. But like some of the rules in chemistry, these are more like guidelines than actual rules. So you could call it like the pirate's code of drawing Lewis structures. But for now, let's follow the rules and draw some Lewis structures. Whenever you're beginning to draw Lewis structures, I highly recommend that you take the time to first draw out the dot symbols of all of the atoms. Let's practice this with CH4. First, I would draw out the Lewis dot symbols of all of the atoms. 1 carbon and 4 hydrogens. And if I draw these well, I can very easily tell by just glancing at them how many bonds each thing will make. The carbon is going to need to make 4 bonds, and the hydrogen will make 1 bond each. The next thing to do is to put the element that makes the most bonds in the middle and add hydrogens around the outside. So I'll do it like this: carbon in the middle and hydrogens around the outside. And now each of my carbon electrons is shared with a hydrogen, and each of the hydrogen electrons is shared with the carbon. Another way you could draw this is using the lines instead of the pairs. And this is the way I'd like you to get used to drawing your Lewis structures. And this is the way that Sapling will also ask you to do it. Now notice our normal bonding schemes are obeyed here. We're obeying the rules. Carbon has 4 bonds, and it has 8 electrons in its octet, 2, 4, 6, and 8. And each of the hydrogens has 1 bond and 2 electrons in its octet, 2, 2, 2, and 2. The other rule that's really useful to know is that basically you want to make sure that you have the same number of electrons in your Lewis structure as you started with. So over here we started with 4 from carbon and 4 from hydrogen, so 8 total. That means we should end up with 8 in our Lewis structure, and we did 2, 4, 6, 8, or 2, 4, 6, 8. So we're following our common bonding schemes, we're not violating any rules, and we're conserving the number of electrons. So this is a good Lewis structure. Now let's try another one, NH3. First, draw the dot symbols for nitrogen and the 3 hydrogens. Now put the atom that needs the most number of bonds in the middle and add the hydrogens around the outside. Make sure all of your elements are following the bonding schemes. In this case, nitrogen has 3 bonds and it has a full octet. So it has 3 bonds in a lone pair and it has 8 electrons around it. And each one of the hydrogens only has 1 bond and each hydrogen has 2 electrons. Also, I've conserved the number of electrons. I started out with 5 electrons from nitrogen and 3 from hydrogen, so a total of 8. And I've ended up with 8 in my Lewis structure, 2, 4, 6, 8, or 2, 4, 6, 8. So all of my bonding schemes are correct, and I've written the right number of electrons, so this is a valid Lewis structure. Now is a good time to pause the video and complete the questions that are on this part of the activity for practice. Make sure to check your answers against the key. We're almost done, but before we go, I'd like to point out a common violation of the normal bonding schemes, basically when the rules don't apply. Now, I'd like you to remember that nitrogen usually makes 3 bonds, and it usually has 1 lone pair. Here I've drawn nitrogen with 4 bonds. This is a common violation of the rule. When an atom is violated, though, and it has 1 more bond than it should have, it will always have a positive charge on it. So nitrogen with 4 bonds has a positive charge. This is called the ammonium ion, and you will see it frequently. Another common bonding scheme violation is when oxygen has 3 bonds and 1 lone pair, instead of its normal 2 bonds and 2 lone pairs. Once again, when oxygen is violated with 1 extra bond, it will always have a positive charge. Notice that in both of these cases, the atoms still have a full octet, and everybody's happy. The only rule that is violated is the number of bonds and the number of lone pairs. But I cannot violate the octet rule. We're going to talk more about this later in the semester, but the way that these type of molecules form is that basically you take one of the molecules that has a normal bonding scheme and you add a hydrogen ion. Remember that the hydrogen ion has an empty valence shell. And here we have a nitrogen that has a full valence shell and a lone pair of electrons. Basically, this nitrogen is really friendly and it shares its electron pair with the hydrogen so that now the hydrogen also has a full octet, or a full duet in this case. Basically, this bond here used to be a lone pair, and now it's sharing its electrons with the hydrogen. That gives nitrogen a positive charge, and the whole ion in general has a positive charge. Same thing can happen with oxygen. Whenever you have a lone pair and a hydrogen ion, that atom can share one of its lone pairs with the hydrogen right there, and now that oxygen, or that atom that has been violated, now carries a positive charge. We'll talk more about this later, but this is simple acid-base chemistry. Learning to draw Lewis structures is one of the most important skills that you can learn right now so that you can be successful later in the semester. So make sure you practice by completing the check for understanding and doing the reading and problems from your textbook. If you have any questions, please come see me or ask your friends for help. Thanks for watching this video on binary compounds and Lewis structures. Make sure you practice this well so that you have a good understanding. If you have any questions, feel free to post them in the comments, and if you like this video, don't forget to vote.